Hello, everyone. Good afternoon. Good morning. Thanks for joining us in this seminar today. We're going to have Mihai Pavel from IMAR in Bucharest, and he'll tell us about his recent work with Tuomas Tajakka about the projectivity of moduli of higher rank PT stable pairs on threefolds. Mihai, please.
Okay, thank you. First, thank you for the invitation to give this talk. And thank you, all of you, for participating in today's seminar. I will present you today a recent project with Tuomas Tajakka, which concerns the moduli theory of PT stable pairs on threefolds. And to be more precise, we will address this question of the projectivity of these moduli spaces. So as you may know, the interest in these moduli spaces appeared in the context of enumerative geometry through this work of Pandharipande and Thomas. In fact, PT stands for their names. And they introduced this notion of stable pairs in order to construct new or to define new enumerative invariants counting curves on Calabi or threefolds. Okay, so I will say a few words about this in a moment, as I would like to introduce you to this problem and to motivate our study of the moduli of PT stable objects. And after that, I will present you our main results. And here I should mention that the starting point of our project was Thomas' PhD thesis. So he addressed this projectivity question in his thesis, and he showed that there exists a semi-ample line bundle on the moduli of PT semi-stable objects. Okay, and he studied the separation properties of this line bundle. In addition to this, in our recent work, we proved, moreover, that in the case when the degree and the rank of the objects are coprime, then we proved the projectivity of the moduli space of PT stable objects. And I will take you through our proof. And if time permits at the end, I would like to discuss a bit also the non-coprime case and maybe say a few words about application in the context of Bridge non-stability. Okay, so let me start with this introduction. I'll recall the notion of stable pairs introduced by Pandharipande and Thomas. So throughout the talk, X will be a smooth projective threefold connected and will be defined over the complex numbers. Then by definition, a stable pair is given by a two-term complex like here, where F is a coherent sheaf, which is pure in and of dimension 1. So this means that it has no non-trivial subsheaf of dimension 0. So in particular, if you look at the support of F, this will be a pure one-dimensional curve. And in addition, you ask that the co-kernel of S is zero-dimensional. This might seem a bit complicated, but you have to have in mind that they defined these stable pairs in order to count curves. So like a generic example of the stable pairs is given here below. So you can take a smooth curve C in X and the divisor, consider a divisor D in C. Then you can define the following stable pair, where this one is the natural line bundle on C and you push it forward to X, and SD is the canonical section induced by D. So this will give you a stable pair. And of course, you can take D to be empty. And in that case, basically the stable pair corresponds to this smooth curve. Okay, now let me say a few words about these enumerative theories of counting curves on Calabi threefolds. So basically in each of these theories, you have to find a candidate, a right candidate counting curves. So you have to find a moduli space which parameterizes your curves. And on the right side, we have the Donaldson-Thomas theory. So here the candidate is the Hilbert scheme of closed one-dimensional subschemes of fixed topological type, V. Here V stands for the type. And the way Thomas proceeded to define this was to view these closed subschemes of dimension 1 as torsion-free sheaves. So you can take the ideal sheaf of the functions vanishing of these curves. And this one is, okay, it has rank 1, is a stable, gives a curve stable or slope stable, okay, and has trivial determinant. And by viewing them like this, we can show that the moduli theory in this setup has a nice obstruction theory, which allows you to define this the virtual fundamental class of the Hilbert scheme. And by integrating it, you obtain the DT invariant. In this case, since we are on a Calabi threefold, this is a zero cycle, this virtual fundamental class, and you can count the points with multiplicities, and it will give you the DT invariance. And maybe one drawback of this approach is that these close-up schemes might have zero-dimensional associated points, which can be embedded points or can be points outside the scheme. So in this theory, you have to take care of this zero component, okay? On the left side, you basically remove this problem by considering stable pairs. And of course, again, you have to construct a moduli, a good moduli of stable pairs. You have to show it admits the virtual fundamental class, and by integrating it, you obtain the PT invariance. Okay, and then the question that arises is how the PT invariants relate to DT invariants, and this led to the so-called DT-PT correspondence. Okay, I will not spend too much time discussing these enumerative theories, but I will concentrate most on this space PT of X and see how, what can we say about it. So regarding the moduli, okay, in what follows, I will denote by CH the numerical Chern character, and let's fix for the moment this vector where B basically stands for the class of the curve and for their Euler characteristic. And now we will look at the following moduli space. So in this case, I will see the objects as complexes in the derived category of sheaves. So complexes which correspond to stable pairs of fixed Chern character V. So for the moment, this is a set. And now there are different ways of endowing it with an algebraic structure. So one classical way of doing it is by using this theory of Le Potier of coherent systems. So he considered these pairs given by a coherent sheaf and a number of global sections, and he imposed a certain polynomial stability on these pairs, which reminds, I mean, it's similar to the Gieseker stability conditions on coherent sheaves. And by using a GIT construction, he was able to endow this moduli of stable pairs with a projective scheme structure. So this is one way of looking at this moduli. A different way is to view it inside a moduli of complexes. So you can look at the big moduli stack of complexes, which was constructed by Lieblich, and to view our moduli PTV X inside that one. And since you have no, you can show that these objects have no non-trivial automorphisms, and because of that is in fact an algebraic space, which also admits a universal family. So it is in fact a fine moduli space. And this was observed by Pandharipande and Thomas in their paper. And the third thing is that it admits a perfect obstruction theory, which I said before. So this allows for the definition of the virtual fundamental class. Now, after this came the work of Bayer and Toda, which observed that you can, so their work was independent, but they observed that these stable pairs of Pandharipande and Thomas can be recovered through some notion of stability on the derived category of coherent sheaves. Okay, so you can recover both the stable pairs and also the Gieseker stable like ideal sheaves. And then they try to explain the DT-PT correspondence via wall crossing phenomena in this space of polynomial stability conditions. So the stability conditions they constructed. So for Bayer, he called them polynomial stability, and Toda called them limit stability. So I will prefer to use Bayer's terminology. Okay, so let me recall this notion of polynomial stability. So for this, you need two pairs. You need a pair, sorry, AZ, where A is the heart of a bounded structure on the derived category of coherent sheaves, and Z is the central charge, which in this case is a group homomorphism from the Grothendieck group corresponding to A, to this abelian category A, to Cm, such that for any non-trivial object in A, you need that when you take the values with respect to large M, then they have to live in this upper half plane. So this is upper half plane without the positive real line. Okay, it contains the negative. Okay, so with this central charge, you can define a natural notion of stability on the object, saying that any non-trivial object is semi-stable with respect to Z if for all sub-objects you have the following inequality at the level of phases. So this is the phase of ZAM. It has to be less or equal than the phase of E, Z of EM, for M large enough. And in case you ask for stability, you need to have strict inequality. Okay, so this is similar, it's a generalization of Brillouin stability. As in Brillouin stability, you would have a central charge which takes values in C and not in Cm. And moreover, you need also the following Hardan-Narasimhan property, which basically tells you that you can approximate the objects in A by semi-stable objects. So more precisely, it tells you that if you take any non-trivial object, then it has a unique filtration such that the factors are semi-stable, and you have like if you look at the phases, they are in decreasing, strictly decreasing order. It's a phenomenon you probably saw also in Gieseker semi-stability or slope semi-stability and Brillouin stability and so on. And with this, let me now define the PT stability conditions. So for this, I will define the heart as follows. I will take APX to be the full subcategory of complexes which are fitting in exact triangles like this. Okay, and here T is a coherent sheaf which has a dimension less or equal than 1, and F is a coherent sheaf which has so there are no morphism from 0 or 1 dimensional sheaves to F. Okay, and these two will define you a torsion pair on the category of coherent sheaves, and you can construct this heart APX by tilting with respect to this torsion pair, and this will give you a heart of a bounded structure. So in particular, this is abelian. However, it is not here. Okay, I mean, this will pose problem later when you want to construct the moduli of PT semi-stable objects and when you want to study its properties. And let me also say that maybe this is not the usual notation people use. They shift this. It's like F1 E goes to T. But for our purposes, we will use this one since at some point we will want to consider the moduli of stable reflexive shifts inside our moduli of PT semi-stable objects, and so that we don't have to shift, but it's not so important. Okay, now let me define the central charge. So in what follows, I will fix H a very ample divisor on X, so this will be the polarization, and then we define a PT stability condition on X with this polarization as follows. Okay, we have the heart, and the central charge will be given as follows. So is by this formula, but this is very similar to the Hilbert polynomial, but we also have this weight, rho d. okay, which are some complex numbers satisfying some properties. Okay, so it's easier to see them in the following picture. So they have to look like this. Okay, and so if you change this configuration, might give you another polynomial stability. You can recover the dt, what's called the dt stability condition, which will correspond basically to some Gieseker stability, semi-stability. So by varying these numbers, you might get wall crossings phenomena at some point. Okay, but I will not touch this for the moment. Okay, so let me just remark that Bayer showed that APZ with this APX with this central charge is in fact a polynomial stability condition. Good. Now let me say that in the known case of rank 1 and trivial determinant, by taking V to be this Chern character we chose before with beta different from 0, then we recover the stable pairs of Pandharipande and Thomas. So PT stable objects with trivial determinant this Chern class, Chern character, are quasi-isomorphic to complexes like this, where Fs are stable pairs. And of course, in case beta is 0, then there is only one PT stable object, which is the structure sheaf. This is like an example, but we'll be mostly interested in the higher rank case. And now, for the higher rank, we have the following nice characterization of the PT semi-stable objects, which is due to Jensen law and will be extremely important, in fact, for our study. Basically, whenever we want to prove something, we will use this characterization of our object. So this says the following: we will fix a Chern character of positive rank, then any PT semi-stable object of character V will fit in a triangle like this. So basically, we have homological sheaves only in degree 0 and 1, and they satisfy the following. So H0 is torsion-free and 2 Gieseker semi-stable with respect to this polarization H. So 2 Gieseker semi-stable means that is semi-stable with respect to a truncated Hilbert polynomial. I will tell you precisely in a moment. Second, we have that H1 of E is zero-dimensional. And third is that we have no maps, non-trivial maps from zero-dimensional shifts shifted by -1 to E. So in particular, this one does not split, okay? You have no map from here to E. If moreover, the rank and the degree are co-prime, then you know that these are enough to say that, okay, if these are satisfied, then you have a PT stable object. And also H0 of E is slope stable, and there are no strictly semi-stable objects. So this is like a complete characterization in the case of coprime rank, which will be important for our case for proving the projectivity in this case. Good. Now, let me recall this notion of semi-stability on coherent sheaves. So we have the following. For any torsion-free sheaf, F, we will consider the following truncations of the Hilbert polynomial. These are reduced polynomials. So this is the Hilbert polynomial, and then we divide it by the rank. So basically, this will give you the usual Gieseker semi-stability. Then, if we consider, if we remove the zero term, then so we take this truncation. This will give you 2 Gieseker semi-stability. And third, we have slope semi-stability. So basically, you consider only the first two coefficients of the Hilbert polynomial. Okay, so if it's Gieseker semi-stable, it's also 2 Gieseker semi-stable, and it's also slope semi-stable. Now, another property which will be important for us is the following. So recall that if we take a torsion-free sheaf, then you can define its homological dimension, which is the minimum length of a locally free resolution. And then there is this result saying that, okay, if it has homological dimension less or equal than 1, then this is equivalent to the fact that you have no non-trivial maps from zero-dimensional sheaves shifted by -1 to F. So this shows in particular that, let me go back. If you look here, like since you have no maps like this, you cannot have a map from t-1 to this one, since this will give you a non-trivial map to E. So in particular, this H0E has homological dimension less or equal than 1. And another fact is that the reflexiveness, which means that F is isomorphic with its double dual, can be also characterized by a property like this, which I will not use. But so in particular, if it's reflexive, it also has homological dimension less or equal than 1. So as a corollary of this is that any slope-stable reflexive sheaf can be viewed as a PT-stable object because it will satisfy the three properties I just mentioned for PT-stable objects. Good. Now, if this is clear, now let me move to the moduli theory of these PT-stable objects. So in what follows, I will fix the Chern character of these objects, which will have with positive rank, rank of V will be positive, and I will fix a PT stability condition on this polarized threefold. And then I'll define the moduli stack of PT semi-stable object as follows. So for any scheme S of finite type, then we'll look at this groupoid, which will be defined by objects E, which are relatively perfect over S, and such that for any point, the fiber will be a PT semi-stable object of Chern character V. Okay, and you can view this inside the Lieblich moduli space if you want. And now one of the main results about this moduli stacks is the following due to Jason law. So he showed that this moduli stack is a universally closed algebraic stack of finite type. So he showed the boundedness of these families. He showed that this PT semi-stability condition is an open condition, which is not so easy to show when you don't have a Noetherian heart. And he showed, okay, also that you have universal closedness. And in addition, he showed that when you have the rank and the degree coprime, then this is a GM-gerb over a proper algebraic space. So in particular, it is both a coarse and a good moduli space for this stack. So maybe to recall the definition of the good moduli space, this is in the terminology of Alper. So this means that if you take the push forward from the category of quasi-coherent sheaves on the stack to the category of quasi-coherent sheaves on the good moduli space, this has to be exact. And moreover, you ask that you have an isomorphism between structure sheaves. Okay, and then we have the following two natural questions. So the first one is whether we have a good moduli space in general. And second is, when we have it, is it projective? So the second one we will address. And about the first one, as I said, this is maybe not so easy to show when you have no Noetherian heart, but there are these criterions. There is this criterion of Alper, Leisner, and Heinlott, where they said that okay, when you have a stack like this, which is nice, then it admits a good moduli space if and only if it satisfies the properties, that is being as complete and being tetrareductive. So one might try to prove that by hand. Okay. In other cases, when you know, for instance, that this PT semi-stability conditions comes from some Bridgeland stability conditions on threefolds, for instance, when it comes maybe from some double tilting, and you know that the heart is Noetherian, then you can use some of their results to show that, in fact, this admits a good moduli space. But in general, we don't know for the moment. Good. Now, let me move to our results. So I'll start by stating them. So we fix the churn character, which will be of positive rank, and we fix PT stability condition. Then we have the following. We show that there exists a globally generated line bundle, okay, non-trivial, okay, on the moduli stack, which separates slope-stable reflexive sheaves. And second, we show that when the rank and the degree are co-prime, then the coarse moduli space, which exists, as I said, is projective. So in what follows, I will take you through our approach and the proof. So let me say that since we have no GIT construction for the moment for this moduli, we have to construct some explicit line bundles on the moduli stack, and then we studied their positivity and we show it has sections which are it has enough sections to separate points, in the end getting the projectivity. Okay, so in general, there is this way of constructing line bundles. So you can take any family. In this case, I work with universal complex, and then you can define the following Donaldson morphism. So you can take here any Grothendieck class, you pull it back via Q to this product, you tensor it with E, and then you push it forward down to the moduli stack, and this will give you a perfect complex. You can take the determinant, it will give you a line bundle. So you can do this. This is fine. The only problem is, I mean, how you get sections of this. So for this, we have the following result, which is again general. You can take any complex, and then it has to satisfy the following properties. So whenever you, okay, for any point in this stack, whenever you tensor it with K, when you look at the hypercohomology, this should exist only in degree 0 and 1. Okay, and you also need to have the dimension of H0 to be equal to dimension of H1. This is the first property. If you have this, this will give you a canonical section of this lambda line bundle dual. And second, if you also know that at some specific point you have H0 equal to H1 and equal to 0, then this section is non-vanishing at this point. But this is general. And the way you show this is by, since you have these two properties, you locally, this push forward can be represented by a two-term complex, and you take the determinant of this, and then you glue the sections and it will give you this needed section. The only problem in higher dimension is that it's rather difficult to check these properties, because you might have you have cohomology maybe also in higher degree. But if you are on a curve, then everything is much easier. And this approach was in fact used by Faltings to construct theta sections for the moduli of vector bundles on curves. So let me tell you about this. So let's consider a smooth projective curve C and take just a vector bundle, locally free sheaf of a fixed class nu. Okay, and then take some eta, another Grothendieck class, which has the following properties. So should be positive rank. It corresponds to another bundle, and should be, if you look at the intersection of this, should be 0. Then Falting showed that if E is semi-stable on C, and if you take M large enough, then you can find another locally free sheaf G of class M eta on C, such that you have this property. So when you tensor it with E with G, then it has no cohomology. H0 equal to H1 equal to 0. So this is exactly what you want. Okay, so imagine you have a family of vector bundles or even complexes, such that in one fiber you have a semi-stable vector bundle on C. Then you can at this point. And as another remark, we have effective bounds on this SEM. So this will be useful later in case you want to get effective semi-ampleness results for the line bundles. You will see in a moment. Good. Now let me tell you the way we choose our line bundles. So we choose some determinantal line bundles. So let's fix this Grothendieck classes. We have the following form. Okay, so they are quite symmetric, as you see. Okay, and they are, maybe you saw them before in the case of Gieseker moduli spaces, because these are in fact the line bundles that also show up in Gieseker for Gieseker moduli spaces, and the linear combination of them gives you basically an ample line bundle on the Gieseker moduli space. And there are two reasons to consider them. I mean, except this one that it's reminiscent of the Gieseker moduli space case. Okay, one is that if you intersect this with V, because of this symmetry, this will give you 0. And using this, you can show that whenever you have a good moduli space, then these line bundles descend on the down to the good moduli space. So, and second, maybe more relevant, is that the way these are defined, basically they encode restrictions of the universal complex to certain hypersurfaces or complete intersections. So for instance, here, when you define this with respect to V2, basically here you would restrict your universal complex at each point to a complete intersection of two hypersurfaces, and in this case, to three hypersurfaces. So, and I will make this explicit in an example. So next, the idea is to study the positivity of these line bundles. So let me start with L2. This was, in fact, studied by Thomas in his thesis. So to study this, first, let me say the two ingredients we need to show the semi-ampleness of L2. So we need a Mechta-Ramanathan restriction theorem to restrict to the curve case, and then we use Falting's lemma to basically to obtain the section, to construct the section. And so what it says, the Mechta-Ramanathan, is that whenever you have a slope semi-stable sheaf, then its restriction to a general hypersurface of large enough degree remains slope semi-stable. So we have the following application of this. So if you start with a PT semi-stable object of positive rank, which will fit in such a triangle with F torsion free and slope semi-stable and T zero dimensional, then okay, you can choose a complete intersection of large enough degree, which is smooth, okay, as you want. And then the restriction, you can avoid the zero dimensional locus, and the restriction will be a semi-stable locally free sheaf on C. This is exactly what you want, so that you can then maybe find this section via Falting's lemma. So you have to do it in families. So you have to restrict any family, any PT semi-stable object, and sometimes, I mean, the divisor will go through this T. So you have to take care that after the restriction to the curve, when you look at the hypercohomology, it will still be only in degree 0 and 1, so that you can apply that lemma. But before that, let me say how L2 relates to a line bundle for a family on curves. So I will take C to be such a complete intersection of two hypersurfaces in this linear system. Then we have the following result. So this is showed directly, like, and it doesn't matter so much how this is defined, but it's chosen such that we have this isomorphism. And what's important is that this has the rank of minus W restricted to C is positive, so it corresponds to some vector bundle on C. And moreover, when you intersect it with V restricted to C is 0. Say exactly the two properties you needed in Falting's lemma. So now let me tell you how Thomas proceeded with this and how he showed the semi-ampleness of L2. So he basically chose a point, E0, and then by taking some general curve of large enough degree, you know by the Mehta-Ramanathan restriction theorem that this restriction is just a semi-stable vector bundle on C. Then by Falting's lemma, you can choose M large enough that there exists a locally free shift G of this class minus M W restricted to C, such that when you tensor this restriction with G, then this has hypercohomology equal to 0. Now for any other E, he showed furthermore that the intersection has hypercohomology only in degree 0 and 1. Okay, he had to work a bit for this, but after that you get, by that lemma I mentioned, you get a global section for L2. Okay, so which is non-vanishing at 0. So basically you get the semi-ampleness of L2. And moreover, you also have some control, because I said we have effective bounds for M, and we have effective bounds for A, because this is Mehta-Ramanathan restriction theorem. Okay, the way they gave it in the beginning, it had no effective bounds, but then there are other variants of this, like Flanner's result of or Langer's restriction theorem, which are effective. So you can use this to get some effective semi-ampleness for L2. Now, he proceeded and he studied how this L2 separates points. We have the following result. So if you take two non-isomorphic slope-stable reflexive sheaves of class V on X, then there is a power of L2 that separates them. So the idea is straightforward. You just cut with a curve, a general curve of large degree, such that this maps between the homes is an isomorphism. So basically, if these are non-isomorphic, then they will remain non-isomorphic. And by Mehta-Ramanathan again, you can show this remain slope stable as well. So you will have two non-isomorphic slope stable sheaves, locally free sheaves on the curve. And now you can use the following result, which separates. So this comes again from the moduli theorem curves, where you can find theta sections which separate non-isomorphic stable points. So I think I saw this in some paper of Estevez. So for M large enough, there is some locally free shift G, so that you have these two inequalities, these two equalities. So this means that you can find a section which is non-vanishing at E1, but is vanishing at E2. So you get a separation. Good. Now, let me move on. We will next study the fibers of this. So besides this result of the separation, Thomas gave a more refined description of the fibers. Maybe it's a bit technical, so I will not explain it now, but I will move forward and study the positivity of L2, of L1 and of L0. So for this, I will assume the existence of the good moduli space, because we want to go and show the projectivity in the coprime case. So I will assume the existence of the good moduli space, and I will consider this map phi, which is defined by L2, and I will take some point here and consider the fibers. So I will study the positivity of L1 now on the fiber MP. So the strategy is as before, but now we don't restrict to curves, but we restrict to surfaces. And for this, we need again two ingredients. One is a Mehta-Ramanathan type restriction theorem, and second is an analog of Falding's. So this is given by Alvarez, Consul, and King result. So this holds in general. If you take the smooth polarized projective surface, then they show that for M and N large enough, then any N regular pure sheaf on D is Gieseker semi-stable if and only if there is such a complex with U0 and U1 vector spaces, and such that when you tensor F with this complex, its hypercohomology is 0. It's exactly what you want in order to apply that lemma for constructing sections. So one remark here is that, in fact, you can choose M and N to work for all Gieseker semi-stable sheaves of fixed Hilbert polynomial, since you know that they form a bounded family. So you can choose N such that large enough such that all of them are pure, N regular pure. Sorry, not pure, N regular pure. In fact, they are pure, so only N regular. Okay, sorry. Yeah, so they give you some conditions on M and N in the paper. And next, we need the following ingredient, this Mekhtar-Manhattan type restriction theorem that I showed in my thesis, saying that if I take any two Gieseker semi-stable sheaf on X and I restrict it to the general hypersurface or surface, in this case of sufficiently large degree, then the restriction remains Gieseker, it will be Gieseker semi-stable. Okay? So in particular, if I take also E to be Gieseker semi-stable, then the restriction will be Gieseker semi-stable. So this is a generalization that I gave, which works in general for truncated Hilbert polynomials. But it will not hold if you take to be Gieseker stable, the restriction will not remain Gieseker stable. That's clear. But if you take two Gieseker stable, then the restriction will remain Gieseker stable. And with this, we can prove the following. So it's an analog of what we've seen when we restrict it to curves. So if we take any PT semi-stable object of positive rank, which will be in an exact triangle like this, then you can cut it by a hypersurface surface of sufficiently large degree, and then this restriction will be basically a Gieseker semi-stable torsion free sheaf on D. So with these two ingredients, we get the semi-ampleness as before. We construct this section, and in a similar fashion, we show also that L1 separates points like this. So if we take two C points such that their Jordan-Holder graduations of these zero index complexes, cohomological sheaves, say H0 E1 and H0 E2. So if you take the Jordan-Holder graduations with respect to the notion of two Gieseker semi-stability, and if these are not isomorphic in codimension 2, so they are not isomorphic but also are not isomorphic after you remove finitely many points, then you can show that there is a positive power of the line bundle L1 which separates them. In fact, since H0 E1 and H0 E2 are torsion free sheaves of homological dimension less or equal than 1, you can choose these Jordan-Holder filtrations, because I recall you, these are not unique. So you can choose them such that the graduations are still of homological dimension less or equal than 1. So then you just have to look at them and see if they are not isomorphic, then you can separate them. So you don't care about this. Yeah. Okay. Now let me proceed with L0. So in this case, I will assume that the rank and the degree are coprime, and you'll see in a moment why we need this condition. So now I will look again at the map induced by L1 from MP, and I will take any point W and look at this base change map. So this will be the fibers. Then by the previous separation result, we have that the geometry points in this fiber will correspond to exact triangles like this. So now we are in the case when all objects are PT stable. So in this case, because of the separation result, we know that on this fiber, which is connected, know that this will be fixed. So it will be a fixed slope stable torsion free sheaf of homological dimension less or equal than 1. And only this one is moving. So this is 0 dimensional. So, and now you have to look at some X space to show that L0 is ample on this X space. But we have we cheat a bit here because we have a result of this result of Benjis and Ricolfi saying the following. So if we are in the same situation as before, you have F0, some slope stable torsion free sheaf of homological dimension less or equal than 1 with rank R and first-chain class C1, such that the rank and the degree are coprime. Then they show that there is a closed embedding of this code scheme of quotients from x1, f0, x, okay, to this moduli of PT stable objects of rank R and the first-chain class equal to C1. So this sends a quotient to a suitable PT stable object. I've seen this before their work in some paper of Jason Law. I think, if I remember well, he showed this set theoretically. And in fact, we have this closed embedding, which will give in the end some stratification of the moduli of PT stable objects via these relative code schemes. So the idea is, I'm writing here this how this is defined set theoretically. So if you start with any quotient, then you can associate this map. So you have to tensor, you have to shift this by -1 and have this natural map. And if you look at this home from F0 dual to Q shifted by -1, then by duality, this will be in the end isomorphic with this x1 of Q. This is the dual of Q, which is defined here by taking the x sheaf, okay, index 3, Q and OX. So this will give you precisely a triangle like this. And furthermore, you have to show that this is a PT stable object. And here it's very important, the characterization of PT stable objects obtained by Jason Law. It's a step where we need the coprime assumption. And with this, after we take base change via this map, this inclusion of n calligraphic into the big stack of PT stable objects, we will have a diagram like this, where Q1, okay, is the close-up scheme in the code scheme you obtain after base change. And you can show that this is a surjective closed embedding. So we know it's closed embedding, but it's in fact surjective because we know how the objects in N look like. And third, okay, this is just the good moduli space. And now, since this is a surjective closed embedding, if you want to show the ampleness of L0 on N, you just have to pull it back to Q1 and see it's ample here. So that's what we do. We pull it back, okay, and okay, it's pulling back this way. And now we use some properties of this lambda Donaldson morphism. So this is just because it behaves well with respect to base change. And now just looking at this V0V, only this component will be important because Q is 0 dimensional here. I mean, it's a family of 0 dimensional sheaves. So only this part is important, but this is exactly the ample line bundle on Q1, which gives you the embedding in the Grassmannian, shows that the code scheme is projective. So we get the ampleness, and as a corollary, now after we have, okay, the semi-ampleness of each one of them on the fibers, we can show, in fact, in the case of coprime rank and degree, that a combination of them is ample on this coarse moduli space. Here it's important that we work with a proper moduli space. And Let me summarize again why the comprime assumptions is important. So we needed it for the existence of the good moduli space because at many steps we consider the fibers. Okay, maybe this is not so much important for the fibers, but we had some control on the fibers. We give some description of the fibers, and for that we had to use powers of these line bundles. And in order to, let's say, to find a suitable high enough power, we needed to work with proper good moduli spaces. But the good model, the stack, sorry, the stack of PT semi-stable objects is not proper. It's only universally closed. So because of that, yeah, it was uh, to simplify, it was easier for us to assume the existence of the good moduli space, which is proper. And then we needed this characterization of PT stable objects of JSON law. We used it at all steps. And in the last step, it was important to have it both ways. So all the PT stable objects are completely determined by the third properties, the three properties. And in the end, we used this embedding result of Benji's and Ricolfi, which maybe is not necessary, but okay, we showed it like this for the moment. And now let me finish with some questions. So first question is whether we can find effective bounds for the base point freeness of these line bundles. So I think we are able to show it for L2, but we didn't think much about L1 and L0. One problem with L1 is that at some point we had to use this restriction theorem. And the problem is the way I showed it is using the approach of Mehta and Ramanathan. And so I'm not aware of effective restriction theorem for two Gieseker semi-stability. Okay. Then it might be interesting to study the Neff and Ampelkons, this moduli space. Maybe study the projectivity in the general case. So I am thinking now with Thomas how we can generalize our construction. We made this assumption on the comprime, on the rank and the degree to be coprime. We think it's maybe not necessary because we have the description, the characterization of PT semi-stable objects, and we think this is enough. And the last question is how this can be applied to Brisna stability. Maybe this will interest some of you. So I've seen in a recent paper of Jardim Law, Machiocha, and Martinez that when X is a smooth projective threefold, so they consider this case of pika rank 1, and they studied this DTPT correspondence via wall crossing in the stability, like the space of stability conditions, of Brijland stability conditions, since in this case you know that you have Brijland stability conditions. And they described the wall crossing. So you have, let's say, a chamber where you get DT stability, which corresponds basically to Gieseker moduli space. You have another chamber for this moduli space of PT stable objects, and you have a map onto the moduli space for a Brijland stability condition on the wall. This is the one here. So which is in this case is defined as follows. You take E and it will be sent to this sum. So this is the S equivalence class H0E plus H1E shift by minus 1. So, and they give a precise description of these objects. They say they are in S equivalence classes with objects of the form F plus T minus 1, where F is 2 Gieseker semi-stable and T is 0-dimensional. So I discussed with Thomas on whether we can show the projectivity of this moduli space. And we think that our approach is feasible, like we can make it work. There's I mean, I'm not promising anything, but we believe our approach should work to show this is projective as well. Yeah, and I will finish here. Thank you.
Thank you, Mihai, for your excellent talk. Let me stop the recording and then, well, let's thank the speaker.
Thank you.
Stop the recording.